Yeah, good morning, everyone. My name is Benjamin from UCD, Ireland. I'm speaking on behalf of my team, Tobi, Gerald, and Ahmed. So basically, we today we've been to the Asian cities. So in the next 10 minutes, I will take you to Africa. So we're looking at the potential implication of different local climate zones products on local climate of a tropical city using Lagos as a case study. So basically, we're looking at the urban canopy parameters of each local climate zones, and then we compare it with locally derived urban canopy parameters taken from our fieldwork. So population generally have been urbanization generally have been unprecedented, and in the next century, it is expected to be concentrated in this part of the world, which is sub-Saharan Africa. So, and we all know the impact of urbanizations, and then there have been few urban climate studies over this region. Possibly, this is because of lack of sufficient high resolution data for urban climate studies. So now we have transferable state of the art models that can be used instead of high resolution observation data. So, so the main problem is now we have the local climate zones, which we can use to drive all these models, especially the urban canopy parameters, which are lacking in this part of the world. So, and then the main problem is that now we have highly heterogeneous landscape in this part of the world. So, ranging from shackles of roads, muram roads, untarred roads, asphalt roads, high-rise buildings, and then circles of dense views of low-rise buildings with corrugated height sheet. So now we want to know how much confidence we can have in using the generic local climate zone scheme to drive urban canopy models. These are examples of the UCP that we have in weather research and forecasting model. So this question might be difficult to answer because we have a range of values in the UCP of the local climate zone scheme. So basically, I have used the default that we have in WAR and then compare it with the fieldwork. First, we generate the local climate zone of the city using our own locally derived training areas, and then specifically for LCZ7, which is the informal area, we have shape files of slum areas, which which we use to represent LCZ7 as informal settlements. So Lagos, Nigeria is in the tropical savanna climate. The mean temperature of the city is between 33 and 25. 33 in the driest month of the year, which is around February and March, and then 25 in the rainy season, which is around August. Population is about 23 million as of 2015, which increases about 3.2% every year. And the population density is very high, like 3,500 square kilometer per person. So, which makes it one of the densest city in the world. So, for our feed in our feed campaign, we have 50 locations which are strategically distributed among the local climate zone schemes. So, for example, now we have more measurement locations in LCZ3, which is the largest of all the areas. And the measurement point within each LCC depends on the size of the local climate zones. So on the feed, we use this locus map for GPS tracking, mapping, and all of that. And then we take measurement of the basic urban canopy parameters, the building height, the road weight, the sky view factor, and then we observe the materials of the urban fractions, the bricks, the asphalt roads. We take observation of that. And then we compare these values with the range of values that we have for the local climate zone from steward, and then we the impervious surface layer we couldn't derive that on the feed, so we use the global map of impervious surface layer, and then we also compare that with what we have in the blue error bars are the range of values we have for the local climate zone, the genetic pattern. So here we see that all most of our values falls within that range. So the problem will be which of those values. So that is part of the question of we're trying to solve. We're trying to have a final range of values for that type of uh, a final or specific values for that type of region. So we compare for the thermal and radiative properties. Since we have, though it's somewhat very subjective because it depends on the observer, and then we use the thermal properties from Van der Waal and Bronze 2020, and then we compare it. We use that one to derive this one multiplied by the percentage or the fractions of the materials that we have from each measurement location. So the red dots are the average thermal properties we have in the weather research and forecasting model that is also copied from Berensov and Brosser. So basically, we observe that most of our parameters are either far below or higher than the generic pattern. For example, we have the emissivity of the roof, which is far lower than the generic pattern, and then the albedo of the wall, which is also very low. So we tested this using the weather research and forecasting model. We use the default and then the one we have from the feed. So we have two simulations from the field work and the generic pattern from Stewart and Ork. So four domains are configured with the weather research and forecasting model with the innermost domain at around 300 300 meters. So for some of the results, we compare it with three observation data from standard meteorological stations. The green diurnal patterns is the one from the fieldwork, and then the red is one from the generic local climate zone, the default that we have in weather research and forecasting model. So basically, you can see that our fieldwork is lower compared to even the generic local climate zone scheme, and the black line is the observations from three stations, two in the core urban areas, and then one in LCZ, which is a rural area. So we also compare the relative humidity. We say that our observations is closer to our field work is closer to the observation than the generic local climate zone. So generally, we see that they have similar pattern of uh, linear correlations greater than zero point 0.9, except that for this station, which we have lower values of air temperatures from our field work. The reason could be okay. Let me show you this first. This is just the overall variations of the pattern, and here generally we can see that the brown box plot is the default, and then our field work is the blue. For the hair surface, for the hair temperature, and then the last surface temperature, we see that for all the local climate zones, our field work is lower than the generic local climate zone scheme. So we also look at the diurnal pattern, the mean diurnal pattern for each of the local climate zones. And we see that in Hall, this is the land surface temperature. We have a lower diurnal pattern, which are even more significant especially during the day in Elizabeth 3, Elizabeth 2, and 1. This could be because uh, we have, for example, in Elizabeth 1, we have like 100 meters of the building height. And then for the generic pattern that we have involved, the default, we have just 37.5 meters. So the difference in the building height would be responsible for this, even more than the thermal properties. So the land surface temperature, we compare it with modest land surface temperature, And then we observe that our fieldwork have some lower bias and root mean square error in terms of the land surface temperature. So this pattern of land surface temperature have significant influence on the air temperature as well. It follows the same similar pattern in all the LCZ, where we have significant difference in the daytime air temperature in all the local climate zones. So we evaluate this based on the data we have from three meteorological stations for air temperature, for relative humidity, for wind, and for land surface temperature. So we found that for air temperature, the bias is not reduced even from for our fieldwork, and then the root mean square error is also not reduced. However, for relative humidity, it is it's fine. Our fieldwork is better, and then for land surface temperature, it's also better. So we used a simple paired t-test to see if there's any significant difference in the root mean square errors of all these variables. So we found that the difference is not statistically significant at 95% confidence level. So the key insight here is that the fieldwork, we want to improve on this fieldwork because this is those 50 stations, which is, and the city is largely heterogeneous. We want to improve on that and also improve on the physics behind the models. So, and then we can conclude that the difference in using the fieldwork based on this is not statistically significant. So I will stop here. Thank you very much for the time.
Thank you very much. Okay, we have about a minute left or so. So we have a question for Benjamin? No? Okay, let me ask a question then. You didn't give us any details, for example, as to how you, because you got very big differences between what was in the table of standard values and what you record in the field. Can you explain the differences? So, for example, the albedo was much lower that you were recording.
Yeah, our the albedo was lower because we have more of untarred roads, muram roads, which I think will have uh, lower albedo than the asphalt roads. So much of the area, much of those local climate zones, especially in the LCZ7, we have those type of roads.
Okay. So I see a question here.
Thank you. It was a really interesting presentation. And actually, we want to understand how LCZ works. So, in the direction the work is doing. But I'd like to understand more about your field program, how long it continued, and what all. So, what was the length of period for which you measured this data?
The setup?
And for how many LCZ?
Yeah, it's for the urban LCZ. We focused on the urban LCZ, and we have a team in Nigeria at Federal University of Technology, Akure. So this one is, I think, is the experiment is still ongoing, right?
I think she's talking about um, the validation data, the observation data. How long was it?
Observation data.
Observation data.
Right.
It's okay. It's for the whole of the simulation period for a heat wave period, which is 5 days in March 2020. Yeah.
So that is one season or 1 month.
Just
One-
five,
one-
just
5 days.
just 5 days. Yes.
And rest, when you say the field input urban parameters, so that's based on the field program. You do the morphology and other parameters by surveys, and, and and you add it to your inputs, or
You mean the thermal properties?
say in the model inputs, one is the going to LCZ. Okay. So do you also cross check the LCZ with your own field survey, or just go by the default LCZ parameters in the model?
Yeah, I go by the default LCZ parameters. Though we have options to either we can. That's why I said earlier that the question is difficult to answer because there's a range of values. So the idea is to just have a final or a specific values that we can develop for that type of region that anyone could use.
I'm going to told it Oscar, right? I'm not just to stay on time with everything else, unless you want to make a statement rather than ask a question.
Ask the question.
Is it a hard question?
It's an easy one.
Okay.
Thank you, Dylan. Did you think of like thinking thermal properties? No, sorry. The measurements you took, are there some that are just next to the weather stations that you use for evaluating your model or not? Because I think you should think about. It's a question statement. Sorry, Gerald. Yeah.
Strip it down to an essence.
No, it's a statement.
The question is, did you get the thermal property information for where you actually
At the
have the
site where you
observations?
evaluate, yeah.
At the site where we evaluated the
Yeah.
data, yeah, I would say yes. Yeah.
Okay. Thank you. I'm going to bring this session to a close just to be on time with everything else. The title of the session was A Decade. That's just 10 years, 11 years since WUDAP began. In fact, I don't think it had the name WUDAP until about halfway through that period. The main purpose behind WUDAP was to create data that people could use for either modeling and observations, and I think it's on the path to achieving this. It is basically a community, it's not funded by anything, but it's an outcome of the IUC organization. If I go right back to when local climate zones, for example, came to play, I think the key thing that lexicon is provides with is a language for discussion. I don't think it's creators would describe it as perfect. We should always reevaluate it in terms of its benefits. But I do think it's provided us a common platform where we have a discussion about global modelling, discussion about field work in a city, a discussion about global risks, and all within the same session. So I would say this is a big positive outcome of the WUDAP project. So I'd like to thank you for your attendance and enjoy the rest of the conference.